Hello. Hello. Hi, can you hear me?
Yes, sir, you are audible.
Yes.
Okay. Okay, so maybe we should start. People join us slowly. So before we start, so any doubts, questions about whatever has been done so far?
Yes, sir.
Yeah,
So,
go ahead, one by one. Yeah.
so in passing, you mentioned that the lower bound for average case in searching is theta of log n.
Right.
Can you give some hint as to how to show this? I was unable to do it using decision trees.
Okay. So hmm, okay, first of all, so let's say that it is much lower than log n. Right? Then
Okay.
can you say how many of them? So it's the average, right? Average over all possible inputs, right? So, can you say that okay? So not more than this many fraction of them can be more than this, can be more than log n by 2 or something. Can you say something like that? So what is this thing that we have used actually? We have told that okay, so we have used this worst case. Worst case is log n. So we just kind of prove that the worst case must be at least log n. So that means there exists at least one input for which you need log n depth of the tree, right? But now let's say that let average case be log n. Because average case be something much lower. Okay, just I'm just taking up some function. Say even say log n by 1000. Okay, if average case is log n by 1000, okay, it's an average over all possible inputs, right? Average over all possible different kind of inputs. So basically there are this n output, n things are there, right? So what can you say about the, so is it possible that almost everybody, is it possible that for almost all inputs the runtime is something like say log n by 1000? But of course I know that, but the worst case is still, but the worst is log n. Is this possible?
I understand what you mean. So you're saying
Yeah.
that if 1 point lies, even 1 point lies above like a certain average, the average would be shifted downwards if almost all of them were small. But that can't happen.
That can't happen. So you will end up
Right.
proving that actually lot of them will have lot of high runtime. Take it from there.
Okay. Okay, sir. Understood. Okay. Thanks.
Yeah, somebody else was asking something. Oh, did I share something? Oh, sorry, I did not share. I was writing something without sharing.
Yes, sir, you were not
Sorry.
sharing.
Yeah. So yeah, so some other questions. Actually, we will be doing this kind of average case thing a little bit more maybe when we do a something about quicksort and all. But you guys should try to think about it. How to get this lower bound of log n for the average case. Yeah. Any other questions?
Sir, and regarding improvement of space complexity of insertion sort, so the trick is just to sort in place, right? So just shift everything every time you sort within the array.
Right. So insertion sort, you can do it in place by kind of whatever space, whatever things you're taking out, you kind of use the leftover space or whatever space is being created, you kind of do it like that. So in fact, if you okay, so maybe I can just maybe here's the yeah. So this, like say, this is one particular something called insertion sort. Okay. Now, so this is basically the insertion sort that we did, except that it is slightly differently formulated. Okay. So yeah, say this is the one. Okay, so sorry. So this is the one insertion sort thing. So basically, what you do is that you have this array in which I will have a kind of a marker. That marker might be some kind of a match thing. The main idea is that everything before this, on the left hand side of this one, I will think of them as sorted. So this is sorted. Okay, so this is the sorted area. And these are the unsorted area. So what I will do is I pick up one element from here. Okay, so let A. And now my job is to put it in the right place for here. So how do I put it in the right place? I can find out that right place by binary search and then move this whole chunk and then place it. Or I can just keep on swapping it one by one over here, right? I can slowly move A downwards and end up finding the right place. Irrespective of that, I will do something of that form, right? And then once I am done with this, I will take this thing and say that, okay, now up to this much I have done. I will shift my indicator, which says that, okay, now up to this point, I am sorted and things beyond it is not sorted. So see, what I'm doing is that I'm picking up one element every time from the unsorted list and putting it back into the sorted list, right? That's the insertion sort. Now, what technique I'm doing it is up to, that's a different thing, right? But I'm doing it slowly. And this is done in place. So I'm not using any extra space because every time, so I'm using only this array of size n. So this is exactly, say you can see something of this from here. So this is the insertion sort where you don't use any extra space. So is this clear?
Yes, sir.
Okay, so some other questions? Any doubts? So in the last class, I know that Sayantan did some asymptotic notations and recurrences, right? So did you guys follow them? Because we will need that thing very much in this course. Okay, it seems that I am not getting any response from anybody.
No, yes, sir. We did follow them.
Okay. Okay, so let's start with today's lecture then. So today's lecture is actually a very important lecture because this is the thing that you guys have seen it in some sense already, possibly in some other settings. But when we talk about algorithms, okay, this course of algorithms, there are a few ideas that our brain doesn't think naturally, but we should start thinking naturally whenever we are to think about these algorithmic aspects. And today we'll be talking about one of those particular techniques. So here, what you can see in this screen is this insertion sort, right? Everybody comfortable with this insertion sort?
Yes, sir.
Okay. Now, what is the runtime of this insertion sort? Maybe I should ask questions now individually. Because now I don't think I'm getting really irritated by people not answering. Urmit, Mahida, are you there? Okay, you're not there.
Yes, sir.
Hello.
Yes, yes.
Are you there,
Audible, sir.
Mahida?
Yes,
Yeah,
sir.
but then you don't answer anything. Why? Okay, so what is the runtime
No,
of
sir, I noted
instruction
yes,
sort?
sir. Order of n
Yeah,
square,
what is
sir.
the in the order of n square? Why? Can you just explain why?
Sir,
Hello?
because we are we are shifting like we are sir, I understood, but I'm not able to explain.
You have the pseudocode right in front of you. Can you explain by looking at the pseudocode?
Yes, sir. Means what we are doing, like suppose we have an array. So by element we are doing comparison, and then we are shifting one position ahead, and then we put that element into the sorted array. So we keep on doing this, and then we finally have an finally we get an sorted array.
Okay.
So for a given I, the internal while loop will have to run I times.
Right.
As I
Exactly.
ranges from 1 to n, it will be n into n plus 1 by 2. Oh, 1 to n minus 1, it will be n minus 1 into n by 2, but still order n squared.
Yeah. So let's look at it. Okay. So there's two ways of thinking about it. When we're talking about an upper bound and a kind of a tightness. Okay. So first of all, for an upper bound, to prove that this algorithm insertion sort runs in times ordered n square. Why? Okay. Why? Because you have this while loop that is running from I equals to 1 to n. Right? Or n minus 1. So there is a while loop of length n. So n times this while loop runs. And now inside each while loop, you are going to keep on swapping, right? You are going to take this j, and j keeps on going down until it becomes, of course, 0, right? So, and j is at most n. So this internal inside each run of the while loop, you can take at most order n steps, because there's another while loop on top. Okay, where this is so is while j equals to 0 and j starts from I, which is less than n, and j keeps on going down every time. So this while loop runs for n times. So the outer while loop runs for n times, the inner while loop runs for n times. The total thing runs for n times, and other than the while loops, everything is taken constant amount of time. Right? So it is order n square is the total runtime of this algorithm. Now you can make it even tighter to some level, because you can say that, okay, while the outer while loop runs for n times, the inner while loop runs for only I times, where I is going from 1 to n. So for I equals to 1, this while loop takes order 1. Y equals to 2, it takes order 2, and so on and so forth, right? So the total time taken is order 1 plus order 2 plus order 3 till order n, which is actually, again, if you can see it, it's also order n square for this. When you have such kind of an algorithm where you have a pseudocode that you have written, where you have while loop, for loop, and such kind of stuff, okay, you estimate the runtime by going by loop by loop. Within the while loop, or before the while loop, or say within this small while loop, these are called linear straight line programs, because they are not doing anything. There's no while loop or for loop. So inside this while loop, it's a straight line program. And then there is so in straight line program, meaning every line you can think of takes order 1 step kind of stuff, right? So overall takes order n square steps. Okay. So is this clear? Okay, I am sure nobody will answer. So Sucheta Bhalla.
Hello, sir.
Yeah, yeah.
Sir, in this array, we are considering indexing from 1, right? Or
Yes,
0.
I'm considering indexing from 1. Yeah.
So then in the while loop, inside while loop, shouldn't j be greater than 1?
Maybe you are right. Yeah, so it should be greater than 1. That's true. Yeah, this should be greater than 1. Yeah. Okay. So this is a way of doing a program. Okay. Now, what I wanted to talk about today is that you can visualize this algorithm. Yeah, some questions? You can visualize these algorithms in another way. Okay? And this is something very, very, very essential. So when somebody gives you a task and okay, how do you go about it? Right. So be organizing some, you want to organize a party in your house or in your institute or something. How do you go about it? What do you do? So how many of you have organized a party? Can you please unmute yourself and say? None of you have organized a party.
Get resources.
Okay, you first get resources.
No, first, sir, we will check how many people are coming. Then we will like organize resources.
Okay, what kind of resources?
So first we need to make a plan of what all we would do in the party.
First, you
and
make a plan of what all do you do in the party. Okay.
like a general idea, then get what participants would be coming, and then make the
Okay.
plan a bit more precise. Maybe either gather the fund at that point or keep it for later for redistribution, and get all the resources and foods, etc. for the thing.
Okay. So you
That's all.
guys have all come
Like-
from, you have all done your undergrad somewhere, right? Say in your college there is a fest. Okay. What is the first thing you do before all of this kind of stuff?
So find a space where we can organize the event.
Okay, who finds it?
So that generally
Like appoint a committee.
Appoint a committee. This is always the first thing that you do. You split the work up. You are telling a lot of things, right? But you, as an individual, you are not doing all of it, right? You split the work into small committees. You say, okay, the committee, your job is to go and find a space. Okay, here is another committee, your job is to go and find money. Okay, here is another committee, your job is to find participants. Here is another committee whose job is to go arrange for food. Here is another committee whose job is to go and prepare for the stage or something like that, right? You split the work up. Now, this is the crucial aspect of algorithms always. Okay. From now on, whenever you think about algorithms, you think about splitting the work up. Okay. A algorithm cannot, the algorithm is like organizing a party. The algorithm is like doing something in a step-by-step way, right? Achieving something at the end. But your job can be to, one of the big jobs is to split the work up. Now, this work might have intersection with them. They might have to talk to each other a little bit, right? You might have to, one supreme committee might have to coordinate between them, right? All of these are fine, but at the end of the day, the splitting becomes an essential thing here. It's a task of breaking up this whole problem into smaller parts. So if I can say that one major part is, okay, algorithmic techniques you can think of. It's almost a 101 of algorithms technique is split the work into sub parts or smaller parts. And then crucial aspect about what is a part of the committee. Why do you create a committee? The person who has created the committee, if that person is not within the subcommittee, he should not poke his, he or she should not poke his nose in that committee, right? Committees matter. So I've created a committee who says that, okay, go and find out space. Now, if the committee comes up and says, okay, here is the best space that we have found for the organizing the party, I mean, somebody else should not poke his or her nose into that. Right? You have to believe in that committee's work. You have to believe that this committee has done a good job. Else, nothing works. Right? So, in some sense, you don't want to go into details of what happens. You want to just find out deputies to do that work. So this is the work of what is called a recursive algorithms. This is a very crucial algorithmic technique that we have to go over multiple times. Okay. So if you are coming from a, how many of you have heard of something called functional programming? Has anybody of you have heard of functional programming?
I
Yes,
have
sir.
just
Yes, sir.
heard of it. Not
Yes, sir.
Sir, in functional programming, there are no loops.
What?
We have to write only functions.
Yeah.
So everything involving loops.
You have to only
or
write
iteration.
functions, which
So
yes.
all loops
So you
should
call
be
the
done by
functions,
recursion.
right? So exactly. So there are programs that have been designed for doing functions, for working with recursive function algorithms.
Haskell does functional programming.
Haskell does that. Haskell, Dr. Scheme. There's quite a few of them in that. But this is a very crucial concept of algorithms. Okay. Now we will come back to this again and again. But say, let's see here. So this is the insertion sort that we had, right? So I can give you a recursive form of this insertion also. And here it is. Okay. So what is it that I do? My job is to sort the first n elements. So I have been given A, and my job is to sort the first n elements. I kind of give it to my deputy and say that, okay, now you go and sort the first n-1 element. I will not do anything. I will not touch anything. You do it yourself in whatever you want. And once you are done, match it together a little bit further, right? So I take the last element and I end up pushing it in the right place. That's all. Okay. So see, now if I have to compute the runtime of this algorithm, what will it be? Now, I am not talking about the correctness of this algorithm, because correctness of the algorithm is basically induction. So if you guys try to solve it, that n-1 does a good job of sorting A in the array A, the first n-1 elements of the array A, then this whole algorithm will work. Means the whole algorithm will end up sorting the array A, the first n elements of the array A. Okay. So that's the So proof of correctness of a recursive algorithm this is usually induction. Because it is almost geared towards induction. That the smaller subcommittees or subparts are working well, and the final stitching or coordinating of the final level works, assuming the subcommittees have done it correctly.
Hello, sir.
Important thing is that I am again emphasizing here, we don't worry about what happens at a much lower level. What is the, maybe you can talk about a base case to some level, but that's it. We don't say that, okay, if I unfold it and all, what happens after that? No, none of it. Maybe the subcommittee has its own super subcommittee and so on and so forth. That's not my job. The proof of correctness goes through straight, assuming that the N-1 level subcommittee manages to do it correctly. Right? Any question?
Hello, sir.
Shoham?
Sir,
Yeah.
I don't know what is
You have some questions? Sorry.
sir, functional program. What
No,
is
you don't need to know function. I was just giving you an example that there are programming, so like C and all, there are programming languages which have been designed to handle only recursive languages. So telling you how important recursive languages are, and recursive not language, recursive programming is. So you don't need to know functional programming. No. So proof of correctness is a recursive algorithm. Is the induction. So our recursive algorithm is basically induction. Now, what is the time complexity computation of a recursive algorithm? How do you do it? Let's go back here. So I'm thinking. Okay. So one way of solving it, and this is almost the unique way of solving it, is that you define, say, the T of n be the time taken by the algorithm when what is that called? So in our case, it is insertion an, right? Now it doesn't matter what the insertion or not, but this is important thing is that there is an n factor over here, and this is what I am interested in. Now, if this T of n is the time taken for insertion n, can somebody tell me what is the runtime of this one? How can you compute it? Can you come up with an equation for this T of n?
Sir, the recurrence should be like T of n equals T of n minus 1 plus B of n. I mean,
Yeah,
so
very good.
normal
Yeah.
n. Yeah.
Yeah. So Pritam Gupta, are you there? Pritam Gupta? Pritam Gupta is not here.
Hello, sir.
Okay. Yeah, hello. You're there? Yeah, can you explain? So your friend gave us an idea about why this can be a recursive equation for computing T of n. Can you please explain why? Pritam, are you there? Pritam, are you there? Okay. I think,
Yes, sir, actually there is a problem with my internet.
okay. Can you Okay. Okay. Pradeep Das, are you there?
Yes, sir.
Yeah, can you explain why this is the case?
Sir, if we assume Tn be the time complexity of insertion sort An, then
Yes.
first here recursion in recursion function we use insertion sort an minus 1. So it is
Right.
t equal to tn minus 1, then plus while
Yes.
loop is up to n. So it is tn
Right.
minus 1 plus order.
Very good. Excellent. So see, this is a straight line program. There is no while loop till now, right? In the if and all. So these are like some constant amount of time. This is constant amount of time that is required. Here there is a call of another function. So this is tn minus 1 on this line. Now there also again there's another line which is some constant number of them, and then there's a while loop. And this while loop kind of works for at most n times, right? So j kind of comes from 1 to n, right? So therefore, the total time is actually t of n equals to t of n minus 1 plus order n. And I am hoping that you guys have seen this kind of things in the last class, then this would become equals to order n square. Right. So this is a very crucial way of seeing algorithms. Now, as this example shows, that insertion sort might be, it's fine to view it as a straight line, as a non-recursive algorithm.
Sir,
Yeah.
sir, can I write TA equal to n plus n minus 1 plus n minus 2 dot dot 1? This is actually the n into n minus 1 by n plus n into n minus 1 by 2. So T of A equal to order of n square.
Sorry, T of n, how are you writing this one?
Actually, we write T of A n equal to n plus n minus 1 plus n minus 2 plus dot dot 1.
Yes, you can do that, but I mean, but when you are writing, you are right. But for which language algorithm are you writing it? Can you just tell me this?
Or
This algorithm or
regression.
this algorithm? Okay, so recursion algorithm, why are you writing it? Can you explain that? So T of n equals to T of n minus 1. So you don't want to write T of n minus 1. Is it? See, I think Dhananjay, this is, so I mean, what you are asking is a very important point here. Okay.
Okay.
When you solve a problem by induction, how do you solve it? Do you try to understand what happens for every possible step of it? No, right? The power of induction is exactly that. Assuming something is true for n minus 1, let's prove it for n. And then you can do it. Now, it is right. I mean, what you are saying is completely right. Okay. You are completely right that when you are calling the algorithm at n minus 1, it is going to call another algorithm for n minus 2. So we should be able to see it as n, then n by n minus 2, then n minus 3, and so on and so forth. Right? But if you start thinking about it in that way, you will not be able to design algorithms. Okay, so that's why I gave you the example of organizing a party. Okay, if you are the boss and you are organizing the party, right? Once you create the committee, you should not think about it. Let the party do it. Let the committee organize that part of it. Now the committee will create another committee, subcommittee maybe, and so on and so forth. But if you try to interfere in all of them, then you will be tired. It's not like that you will be, or if you want to know exactly how the committee has worked out what all subcommittees has the committee created, and so on and so forth, you will be, I mean, nothing will happen. Everything will be fine, but you will be exhausted. Right? So it's not a wrong thing to do, but you will be exhausted. This is exactly here. If you think about recursion, you should think just one step ahead. Okay, as the boss, your job is to split it up into small parts and combine them together. So what you are saying is completely right. That T of n becomes order n plus order n minus 1 plus order n minus 2 is order 1. But this is not what is coming out from this pseudocode. What's coming out of this pseudocode is T of n equals to T of n minus 1 plus order n. Okay. Okay. Fine. So let's look at another sorting algorithm. Yeah.
A question. Yeah. In practice, while using imperative languages, we are discouraged against using recursion because it's slower than just using straightforward iterative version of the same problem.
Yes, but many times you are right. If you have straightforward iterative languages, then it is fine. But most of the time, you'll very soon see that the best algorithms are recursive algorithms.
I see. Okay.
So yes, if you have a straight line algorithm, then fine, go for it. But most of the time, the recursive algorithms are the best.
Sir, can you just repeat why, like in what context you said the recursion algorithms are best? Like, there was some internet issue at my end, I could not follow.
Okay, I will give you examples later on. Like in terms of the best time complexity will be of sorting will be achieved by recursive algorithms. Okay. And there's no other way of using it otherwise. The best time complexity for many problems is via recursive algorithms. And then there are extensions of recursive algorithms using what we call dynamic programs that we'll also study later on.
Sir, there was this question that I had last semester. I'll ask it to you again. I'll ask it to you. It is something related to this. So is it true? So imagine that you have a set of all computable programs which can be written as a recursion. And then you have a set of all computable programs which can be written as an iterative process or a straight line program or just using while loops, or let's say. Is it true that these two sets are equal?
Actually, possibly it is true. Okay. But the issue is that an algorithm is not always looked at, or the importance of the algorithm is not studied.
Sir, can you repeat the question?
Only by, sorry?
Can you repeat the question?
Okay, so basically formulating this question in another way is that if I have an algorithm that has a recursive algorithm, is there a kind of a iterative algorithm for that?
And vice versa.
Is there a straight line algorithm? Yeah, and vice versa. Right. Vice versa, I don't think so, because I think, I mean, okay, you can always, so this is a vague question, because when we say that it's a recursive language, I mean, what do you mean by, I mean, you can always create some lots of weird recursions, right? If I have a straight line algorithm, you can do a lot of weird things to do something, right? Yeah, so let's not discuss this one. It's true that there can be written, but again, very soon we will see some algorithms where this which will be recursive algorithms. They will be having the best runtime among all the possible runtime algorithms, among all possible sorting algorithms.
Sir?
And as such, yeah.
Going back to the previous question.
Yeah.
If both like with both recursive algorithms and with algorithms including say while and for loops, if both of them can perform everything a Turing machine can perform, then both will be equivalent, right?
See, there is no very well studied. I mean, what do you mean by recursive algorithm? Then we have to talk about formal definitions of recursive algorithm. Okay. So when we are talking about Turing machines and all, they are all formal stuffs and all. Okay. So we have to be very careful about those formal definitions. So let's not go into that definition right now. Let's discuss. Okay. I mean, what we are what we are talking about is the intuitive understanding. But if you have to say, okay, define the class of recursive algorithms, then we have to be really careful about formally defining. Okay. So another thing that I must say that while another place where recursive algorithms, okay, so let's put it this way. Okay, another place where recursive algorithms have a formal definition and has been used also, and which kind of is better than non-recursive algorithms, is parallelizability. Okay, so many times, so for example, let me start with a very simple question. Okay, say I have a pile of n numbers, and I want to find the maximum. How will you do it? How will you? So say let's call this one A1 to n. I want to find the maximum of this A1 to n. How will you go about finding it?
One linear scan will do it.
One linear scan will do, right? You can just keep another parameter max, and you kind of check whether AI is bigger than the max or less than the max, and accordingly update it. Fine. Let's say let's ask somebody else. Harshotto Mondo, are you there?
Yes, sir.
Yeah. So what will you do if you
So
are
can you
given
repeat the question, because there is some noise outside, so I didn't listen to the question properly.
Okay, I have another question for you. If you didn't listen to the question properly, why didn't you tell me earlier? I mean, the unmute button is there exactly for that reason. So how much did you listen till now?
So there is some sound.
Sound from my end? It's possible. Is
No,
there
no,
sound
no.
from my end?
From my end, I think someone is drilling his room for some thing. I don't know. There's noise in my hostel.
Okay, but then you should say that. Can you please repeat? Can you please repeat? That is something. Okay. Anyway, so if you are n numbers, how do you find the maximum of? What will you do to find the maximum of these n numbers?
In an array.
In an array, yeah, say in an array.
First, from search, actually doing the comparison, and first we define the first element of the array as the maximum and run a loop and compare every element of the array with that particular element. And
but if you had in real life, what would you have done? Is that what you would have done? If I give you a huge number of, say, numbers, I mean, so each, I mean, there are some lots of coupons, lots of coupons in a bag, and you want to just find out which coupon has the maximum number.
We can use the recursive method. Just break the array from the middle.
Yeah, but why will you do that? Why will you do that? What is the advantage that you will get by doing that?
Because it will take less time, I think. By searching the
Will it
whole
less
area, I
time?
think it will take less time.
It will take less time. Why will it take less time? So what you are saying is that you can break it up into two parts, A1 to say AN by 2 and AN like 2 plus 1 to AN. And you search something from here, right? Why will it take less time? I mean, just think. What I'm on trying to do in you guys' head is that don't think algorithm as just a computer program. Think of it. What will you do in your real life? If I give you a box full of coupons, each coupon has a number on it, and your job is to find the maximum, what will you do? Why will you split it up into two halves and then do it?
Actually, I was.
Yeah.
So we can just like when we see there will be something which bigger number, we just take that and see whether there is something bigger in the collection.
We do some sort of heuristic thing. It cannot be exactly told as an algorithm or something.
No, you do an algorithm. Don't believe me, you do an algorithm. Just you're not thinking in that direction. I can tell you. I will tell you in 2 minutes. But I want you guys to think and think in real life.
Am I alone or do I have friends with me during the
You might have
computing?
friends with you. You can use your friends.
So then we can split it into 4 or 5 parts. As many of us are there, we just get our maximum of our respective parts and then
That is the advantage of splitting. The advantage of splitting is that you can give one to your friend one and one to your another friend, right? And find the max and then combine it. Now what happens? Why is it advantageous? Your friend will take some time, your another friend will take some time, but they will be running it in parallel. So the time taken to solve is not the sum of the time taken by friend one plus time taken by friend two, but it is the max of these two. Okay, so if there is an algorithm like this where you can split it into two equal sized problems, you can give them to two different groups or two different friends, ask them to solve, and then combine the results. By doing so, you are reducing the effective time. Now you might say, oh, but this is when we are friends. What will you do in a computer? So how can it have help in a computer?
So we can break the array into two parts and then simultaneously repeat the process with the left part and with the right part. Because it's happening simultaneously, it's essentially parallelly.
Yes, you can use the different ports, right? You can use the whatever this GPU. You can use various things. Nowadays, everything is done parallelly. You have all the machines are interconnected, right? So this is what is called parallel computation. So any recursive algorithm is ideal for parallel computation. It breaks into two parts. Okay. Is this clear?
Yes, sir. Understood.
Sir, I'm unable to think that how is it less than order n?
Okay, how will you think that order n? Let's see. Even order, what is order n? Okay, so at time t equals to 0, I get an array, right? A equals to a1 to an, right? At times t equals to 1, I split up into two parts. A1 equals to a1 to an by 2, and a2 is an by 2 plus 1 till an. I mean, basically, if I think of it this way, this is a of 1 comma n by 2, and this is a2 is n by 2 plus 1 comma n. Right?
Sir, are you writing
Sir, are
something?
you
Are you writing something? Because
Oh, sorry. Yeah, I'm writing something. Okay. Now, oh, so that's why you did not see these things. Okay, so I had written lots of things earlier also. So now you give it to code 1. You say that, okay, now find the max in what? A1 to n by 2, right? This is at time t equals to 2. But at the same time, you are going to give it to another core on another machine, right? N by 2 plus 1 to n. So this one will take some amount of time, say r amount of length. This one will also take r amount of time. So then this is t equals to r plus 2 or something like that. You find this max. So this is, so it outputs some y1, this outputs y2, and you are outputting, what are you going to output? You are going to output. So this will output, say y1, this is output y2, output y1 max of y1 comma y2. Now, what is the runtime that is happening? If you think of it as a total amount of computation, yes, you are right. It is order 1, 2, 3, three level compute step, 3 steps plus 2r plus 1, right? So the total time is how much? And say r is something like, r is something like n over 2. So total time taken is just order n. But here, when you are doing it, I mean, order not order n, of course, everything will be order n, but it will take it will take n steps. But when you split up into 2 halves, then how much time does it take? Hello?
So it would still be ordered in, right? Because the number of cores is a constant independent of n. But
no, it will be ordered n.
Like
I'm completely agreeing it is ordered n, but it will be
n by
constant
number
in the
of
order
cores.
will improve. Constant
Yes,
in
sir.
the order will improve.
It'll be n by 2. It'll be like just
N
doing
by
half
number
of
of
the
cores.
array.
Yes. N by the number of cores, say something like that. It is not exactly n by number of cores because there is something else. This is something I was going to ask you guys. But how many cores do you want to use?
So it is like we have given two tasks to the computer, and since they are working simultaneously, then it will be n by 2.
Yes, that's true.
Oh, that means 2 people are working for me, and so okay.
2 people are working for you, right?
Okay.
I mean, this is
So why
this
don't
is in the world of
why don't
parallel
we just
computation.
split
I'm
more?
saying that anything that is good. That's what I'm saying. Why don't we split more?
You can.
For that, the number of
in
comparisons will significantly increase for each and every step. Number of comparisons will increase to find out the max.
Like I want to say regarding this. Say suppose I have 100 coupons, and if I split it among 4 people, each get 25, and it's okay. But if I say I have 100 people, and then each get 1 coupon, it returns back to that original problem of comparing 1 by 1.
Exactly. So it doesn't help, right? Right.
Yes.
So it's a trade-off, right? It's a trade-off. You can see it's improving, but how much will it improve? Okay.
The question of
Now,
optimization.
can somebody say what will be the actual value if you do this thing? Yes, it will be actually square root.
Square root.
The square root of m.
If any sufficiently large, do we like really have computers of root n order of code?
Oh man, nowadays we have so anything with I mean, you don't have one computer, but now there are this whole things called this GPU and all things that works in the cloud, right?
Yes. Okay.
So computation is like huge, right? So if, and this is a very natural thing that happens. Okay, so this is a big area of work. Anyways, we will not be spending too much time in the parallelization of algorithm, but I'm going to just, this was an idea about why recursive algorithms are even useful in real life, even otherwise, other than just improving the runtime. Okay, but recursive algorithms can also improve the runtime for straight line programs, kind of stuff like that. Okay, for sequential algorithms, not just for parallel algorithms. So this is exactly what we are going to study now. So this is a very simple concept. If I have, so this is something that again I am going to ask you guys again. What will you do? So you have played cards last time, you told, and many times we have the job of sorting the cards, right, in a particular order. How will you do that? Now this is not that natural, but one thing that can be done is exactly, if I have A1 to AN, I split up into two halves. A1 to AN by 2. And AN by 2 plus 1 to AN. Now I will sort each of them individually. Fine. So I managed to do that, and I produce a sorted list. Okay, so say 1, 3, 5, 7, 9. And another sorted list is say 1, 2, 3, 5, 7, 11. How do you merge them? These two are individually sorted. They parallel. In some sense, I have deputed my friends to do it. I've deputed friend 1 to compute sort this set. I've deputed my friend, another friend, to sort this set. How do I merge them now? I have got this two sorted array. How do I merge them? And this is something that can be done. Why? I can keep on writing. I can keep a counter here. There's 2 arrows. And I will at any point of time, I say, okay, which is the lower of them? Okay, the lower of them is say 1 at this point. Fine, I'll take 1 and I move. Lower of these 2 arrows is which, how much? Okay, again 1. That means this is from this side. So I will move it here. The lower of these 2 arrows is how much? Oh, okay, it's 2. I will move 2. So that means I will move this arrow here. The lower of these 2 arrows is how much? It's 3. Okay, 3. So maybe I will again move this arrow over there. And I will slowly keep on writing them one by one, right? So I will make a linear scan of this side and linear scan of this side, and I can merge them together. So that means if I get sorted list here, I can produce this merged list in order n steps. So this is what is known as the merge sort algorithm. So let's see. I should have it here. Here. Okay. So I'm quite sure that you guys have seen it to some level. So look at the one. First, look at the one on the right hand side. So this is an algorithm that says that I have been given 2 sorted lists, B and C, and my job is to merge them into a sorted set list D. So what do I do? So I keep on updating it. Okay. And I am going to store it in a new D. So this I and J are basically these two red arrows that I am talking about. So they are the pointers that pointing to where I am looking at right now. And at any point of time, okay, so here I have written only half of it. That if Bi is bigger than Cj, then I should, so Cj is the lower one, so I should put Cj in the dk. Okay, so what is the k? I should write what is the k. K is the arrow pointing here. So this is, so if I want to write it here, this is the I, this is j, this is k. And if Cj is less than Bi, then that means the Cj should be put in the dth place. So I'll put Cj in the dth place. I increase j, I increase k, and I keep on doing it. And then there's an else thing which is just the opposite. If Bi is less than Cj. So this is what happens when you merge two sorted arrays. Okay, and when you merge them, okay, after you know how to merge it, so what is the algorithm for this algorithm called merge sort? Okay, it is pretty simple. You want to sort an array A between all the numbers between these 2 points, say low and high. So what do? Okay, first of all, if low and high are same, then you output just that value. There's nothing to merge, sort, right? And otherwise, I take the middle value, I merge the first half of the array, I merge sort the first half of the array, I merge sort the second half of the array. Now the first half of the array after sorting comes out to be the array B. The second half of the array after sorting comes out to be array C, and I am just going to merge them, right? I'm just going to merge these two using the merge algorithm. So is the algorithm clear? Any doubts? Any doubts what's happening?
Hello, sir.
Yeah.
Sir, can you please just briefly once more inside the if and while part?
For this one, for the merge algorithm or the merge
Yes,
sort?
yes. No. The merge algorithm.
Okay. So let's try to see it again in this example, and then I think you'll better understand it. Here, say I have these two arrays, right? Say 1, 2, 3, 4, 5, 6, and the other one is say maybe okay, just for this for our safety reason. Okay, so let's say these are the two merged things, right? So this is B, this is the array B, this is the array C, and I want to create another array of length how much? So B has 1, 2, 3, 4, 5, 6, and C has 1, 2, 3, 4, 5. So I want to create an array of length how much? 11, right? Okay. And what is the one that what I want? I want to make the D to be the merged, I mean the sorted array, which is obtained by the merging both this B and C. So I start with pointing 3 pointers. Okay. What is I pointing at? I is pointing at the last bit that, I mean, so anything before I minus 1, before I should already have been placed in D. That's the idea. J, this is the matter J. Anything before J minus 1, so anything before J must be has been put in D. and this K is where the first empty spot is. So let's see, what do? I am first going to compare Bi and C at any point of time. So is this less than this? No, sir. So if Bi is less than Cj, then what do? Then the idea is that if Pi is less than Cj, then I should basically, I mean, if I want to use a little bit of things, I should take this Bi, put it here, and then kind of say that, see, this one therefore should point out to the next one, and this one should point out to the next one. Okay. Now, if the opposite happens, then what happens? In this case, I should basically take this smaller one and put it here and move over here and K to the next. So at any point of time, what is happening is that I'm pointing, the eye is pointing to the index from which I have not kind of, so anything before I has already been put in T, anything for J has already been put in T, and K is pointing to the empty slot. So this is exactly what is happening here. Okay. Now, is this clear what's happening?
Yes, sir.
Now it is clear. Okay. Now, why is it going to output the correct answer? Maybe this is something that you guys should write or try to prove it by yourself. That why does this D, algorithm D or level D, actually output a correct a sorted array? Okay, I'm not going to prove it. I am making you. Yeah.
So D is a loop invariant. The fact that D is sorted is a loop invariant. It will stay sorted and its size is increasing.
Exactly. Yeah, that's the loop invariant that you have to prove. Yeah. Yeah. So in this while loop, you have to put in a loop invariant. The loop invariant, you can put that D is sorted, and yeah. So that loop invariant will help you to do it. Okay, fine. And so the merge sort is clear now. What happening in the merge sort? Anyway, there any doubt about the correctness of the algorithm or what the algorithm is doing? Everyone understands? Deva Prasad Kundu?
Yes, sir. It's fine.
It's fine?
Yes, sir.
Okay. Rachit Parikh?
Yes, sir. It's fine.
Rachit, it's fine, right? Good. So now, what is the runtime of this algorithm? What is the time complexity of this algorithm? What is the time complexity of this merge sort?
N log n.
Why?
So because suppose the complexity is Tn, so the recurrence would be like Tn equals 2 into Tn by 2 plus B big of n.
Right. So basically, okay. So first of all, one thing is that the merge algorithm is ordered n. Okay. So merge algorithm is order n. I am not going to prove it. You go and prove it yourself. Okay. Now let's look at this merge sort algorithm. The merge sort algorithm. So let Tn be the time complexity when high minus low is n. Okay. When high minus low equals to n. So this basically means that this is the size of A is n, basically. I mean, intuitively, that's the idea. That this is the array that I am sorting a length n array, kind of. So what does this one say? T of n equals to T of n by 2 floor plus n by 2 ceiling. That will be the case, right? So actually it will be T of n equals to T of n by 2 floor plus T of n by 2 ceiling. Yeah, I think this is the correct thing, or maybe it's n minus 1 by 2. You just check it out. Whatever. So obviously I can write it intuitively, or more correctly, n minus n by 2. Plus, I have to do this merging also. So this is equals to order n, right? So order n. So now this n by 2 ceiling, n by 2 floor, and all those things, you can, I don't know whether you guys saw it earlier or not, but for all practical purposes, we can think of this to be T of n by 2. Both of them are T by n by 2. So I can think of, if n is equal to 2 to the power I, or 2 to the power t, some power of t, then this is 2 times this plus order n. So whenever we want to try to solve a recurrence relations, we can always say that, because we are only interested in what happens in for large enough n's and so on and so forth, right? So you can assume that the n has some special property, like say power of 2 and so on. And you can prove, and as long as this t functions are increasing functions, everything is going to work fine. Now, if you have this one, then you have to solve it, and I'm not solving it for you. You guys go and prove it, that this means that this is n log n. Therefore, the merge sort is ordered n log n. Okay. The insertion sort was order n squared, merge sort is order n log n. So you can see how recursion helped to reduce this time complexity so drastically. Okay. Any questions in this direction?
So the space complexity is n, right? The extra
yes,
d.
the space complexity is n. You're completely right. Okay. So this is the worst case runtime is order n log n. You can prove it also that this algorithm, particular algorithm, the best case runtime is also n log n. That's the sad part. Meaning, even if I give this algorithm to be sorted, even the array to be sorted, the algorithm that how I described it here, it would still take order n log n steps. The average case runtime is also order n log n. The space complexity is order n because I have to use this extra d space, this algorithm. I have not, at least not proved to you how can you do that in place sorting. So this is not an in place sorting. That's what I have told you. And this algorithm is highly parallelizable. So I have, so of course, now there's a lot of questions that can be asked here. Okay, like why this order n log n is coming up? Can you do better than n log n? Can you? So the reason n log n is coming up is because this merge sort, there is this merge sort, this merge algorithm is taking order n steps. Do I need to do that? Can I save on this order n steps? Or can I do something else? Okay.
So the lower bound for sorting is n log n as a problem, right? So
okay, I mean I have not
other
yet,
than out.
Yeah, you are completely right. You have jumped ahead quite a lot, but I have still not done the lower bound of n log n.
Okay, sir. Okay.
So there is no way to make this an in-place sort.
It is. So if you actually go and search the Wikipedia page for sorting, you will find that there is a zillions of sorting algorithms. Okay. So I will be posting this particular slide. In this slide itself, you will find there are two other sorts that I have not talked about, the bubble sort and the selection sort. Okay. And you guys make sense of whatever those they are. And but they are just some kind of warm-up sorting algorithms. And then there are other sorting algorithms. We will be doing at least 2 more sorting algorithms in this course, particularly next class, 2 or 3 more. But of course, it will not be possible for us to cover all of them. Now, if you are trying to see what is the most real life applications of, I mean, which are the, I mean, if or what sorting algorithm does Python use, or what sorting algorithm does C use, or something, it is actually none of them. It's a combination of all. I mean, they do a much more finer optimization. That if n is less than this quantity, then I will do something. If n is more than this quantity, then I will do something. And even this merge algorithms also, merge sort algorithm, also there are in-place sorting versions of merge sort. There are algorithms that have better best case runtime. So there are lots of this kind of algorithms that happens, and this is a phenomenon that you will find in many areas of algorithms and its applications. So in the algorithms, in the world of algorithms, what we try to do is that we try to come up with abstract concepts of resources like time, space, parallelizability, randomness, so on and so forth, which are kind of has some real life feeling to it. Okay, and try to come up with the best mathematical way of analyzing a algorithm. That helps us to design newer and cleverer algorithms like merge sort, right? But once we have this nice algorithms, and when it goes back to the engineers to implement it in a particular software or particular real life applications, then they have to do way more optimization part that happens. So it's a kind of a this is a world where a lot of collaboration keeps on happening. So it's not like the engineer's job is just to I mean, the scientist's job is, computer scientist's job is just to create an algorithm, and engineer's job is just to write up the program. No, the computer scientist's job is to analyze the algorithms, the programs, what is the best algorithm, the best correctness, and so on and so forth. Ideally in a mathematical world, so that you have some correctness algorithms and all. And once you have these clever algorithms, beautiful algorithms, it goes back to the engineers whose job is to not only just program, not just take the pseudocode and just program it, but to think about how you can implement it better, understand the architecture of the place where it is being applied, the amount of resources that it has. So there might be some particular settings in which a little bit of extra space is not that much, but time might be more valuable. In some other places, it might be a little bit of extra time is not that much problem, but space is more valuable, and so on and so forth, right? So I mean, in this course, of course, we will be focusing mostly on this understanding the correctness and the goodness of an algorithm, but that doesn't mean that these are exactly how it is being implemented. So we will be seeing this merge sort algorithm, and I will not be doing the special cases of the merge sort. But if you guys are interested, please have a look at this say, Wikipedia page or something like that, where a much more detailed analysis of what all programs is used in the Python code for merging, and all of that will to come up. Okay. But okay, so the takeaway point from today's class is something completely different, as you can expect. It is the fact that whenever you have to think about designing an algorithm, you have to think recursively. You have to think about splitting the problem into smaller parts. That's a major handle that we have on designing new algorithms. And like, for example, this merge sort algorithm is something that is clearly recursive, and we don't know a non-recursive merge sort. There is certainly, you can do it, but you don't. It's like a very recursive thing. It's like this merge sort, you can assume that it is correct. It manages to sort it out nicely, and then it works. Right? You do it by breaking it up into smaller parts and going down. So I think I will go back, not I think, but I will be going back to this recursive algorithm concept again and again and again in this course. So this is a very crucial thing. I want to drill it in your head. Whenever you think about algorithm, one thing that you should always keep in mind that by designing a recursive algorithm might be advantageous for you in certain sense. So think recursive. So this is exactly how, if you guys remember, in your high school, there was a time when maybe your teachers or something had kind of told you that if you have any statement that you have to prove, that for all n prove something, think induction, right? Here also I'm talking about the same thing. Whenever you think algorithm, think recursive. So okay, so any questions, doubts for whatever we have done so far? Okay. Tomolika Ghosh.
Yes, sir. Yes, sir.
Yeah. Did you follow this class?
Yes, sir.
Okay.
Sir, kindly can you send the notes of the last lecture?
Of the last lecture, meaning on the recursive algorithms, recursion?
Board work like slides, whatever you did in the class.
Today's one or the
last one and today, both.
Today's one and the previous one.
Yes, sir.
Okay, sure, I will do that. Okay, so I will stop here today then. There will be a problem set has already been posted. This is on selection and searching and sorting. Okay, some of it is possibly on topics that has not yet been covered, but will be covered in the coming classes. But please feel free to try them even now, if at least if you understand whatever this meaning of these problems are, or the statement of the problem.
Sir,
And
you mean on the website?
In the website, yes.
Okay, okay.
Okay.
Yes, everything will be posted in the website. You should regularly check it. And yeah, you don't have to solve it and submit it. It's for your case. But we will be also be giving you an assignment, possibly end of this week. Okay.
So
yeah,
we already have 2 assignments need to be submitted next week, sir. Can you postpone it by 4 or 5 days?
Okay, I mean, if you post it next week, doesn't mean that it will be submitted next week only. I mean, you can submit it in maybe 10 days time. So it will, you have time. Yeah. Oh, and the other thing is that about this tutorials. Now, come on, I'm a bit confused now. What's going on? The MTech CRS students. I mean, do you want to continue on the online tutorials only altogether all throughout this course, or do you want it to be physical sometime? And similarly is for the MTech CA students. So that's why I understand some of you don't have a hostel, and you guys have requested for it to be hosted online, right?
So for
Yes, sir.
some people have like decided in Barulpur or Habra, and they have to come for tutorial for just at that, and returning at night becomes a problem. So we are trying to fix that issue as soon as possible, and we'll hopefully like to return to physical classes as soon as possible. Just we are trying to sort that issue out at that moment.
This is the MTech CS students, right?
Yes, so this was a temporary solution before that only. Not
Okay, so I mean, to please keep us posted how we want to do it. Okay. I mean, online is fine with us, but I thought that offline is better for you guys. Yeah, you keep us posted, and same for MTech CRS, I assume. Or MTech CRS, have you decided that it will be online all throughout?
No, sir, we will do offline class, but same problem as yesterday.
Okay, and that has not been sorted out, right? Yet?
Yes, sir.
Okay, so you also keep us posted. Okay. Okay, thanks.